Hello and welcome to today's class of week 8 of NPTEL NPTEL Net Communication Networks problem solving session. So today we will be solving problems based on what we taught in week 8 of NPTEL Analog Communications. So we will be starting the topics of ALOHA today and multiple access. So in multiple access we will learn about ALOHA and slotted ALOHA today. So first we will go through the basic concepts and then we will learn basic concepts and then we will learn about the technology that is used in multiple access, and then we will use that technology to solve problems, real life problems. So we will be starting with the basic concepts of ALOHA, random access. So in basically when multiple devices are connected, then we need to create a multi-access protocol such that the resources that are in the network, resources that are being used to transmit in the network, since these resources are limited in nature. So So to our so when multiple nodes are connected in a particular network, then the thing is that all nodes cannot access the network together. All nodes cannot send their messages together because the resources in the network are limited in nature, and thus if one device has to send a lot of data, then what may happen is that it may monopolize the resources. That is, only it is sending the data, and while other users who do not have that much amount of data to send, they will be waiting in a long queue. So this is inherently unfair. So to create a semblance of fairness, so here the main objective in multiple access is fairness. So the main objective here is fairness. So here the main task is to ensure fairness, so that every device can send slash receive. So every device can send slash receive irrespective of the data that it has to send or receive. So this is, now these protocols, there are multiple access protocols. Some are random access protocols, like ALOHA, CSMA, CSMA-CD, and CSMA-CA. Some are controlled access protocol, and some are channelization protocols. So here, channelization protocols might be familiar to you: FDMA, TDMA, CDMA. So here we basically create channels and divide the resource, namely frequency or time or code. We divide this resource into multiple chunks or multiple channels, and then send the data using these dedicated channels. So like each user occupies a particular frequency slot or a particular time slot or a particular code. So this is a channelization protocol. But in a controlled access protocol, we basically control the sequence and manner in which the users are accessing the network resources. So we control access sequence. So here the access is happening in a very controlled manner. So here, like you can make a reservation. So if you want to send your data, you have to first make a reservation, or you can do polling and token passing. So these are controlled, whereas the most basic multiple access protocols are random access protocols. So random access protocols are where simply that are the fact that one user randomly gets selected to transmit the data, and then it sends for a particular time frame, and then another user is randomly selected to send the data. So they are randomly selected, and there is So there is a particular in a random access protocol, there is a particular lottery that is going on. So users are getting selected at random to transmit their data. Whereas in controlled access protocol, there is a there is an algorithm or sequence that is used to decide who will send the data. Whereas in channelization protocol, the existing resources are divided into channels, and then multiple users are transmitting at separate channels. So first we will discuss random access protocols, and then we will discuss controlled access and centralization, or sorry, channelization process. And these all multiple access task is handled by the media access control sublayer of the data link layer. So it is handled by the media access control layer of the media access control, or MAC layer of the data link sublayer, MAC sublayer of the data link layer. So first we will discuss random access or contention methods. Random access methods are also called contention methods. So here no station is superior to another station, and thus they are all at a equal footing. Whoever has to transmit can transmit. So at each instance, a station that has data to send uses a procedure defined by the protocol to make a decision on whether or not to send. So whenever the user has a data to send, it will it will consult an algorithm and make a decision of whether to send or not to send the data. This decision depends on the state of the medium, whether the medium is idle or busy. Now two salient features of random access are that there is no scheduled time for a station to transmit. So there is no schedule. There is no schedule. It all happens in a haphazard manner. Whoever has a message to transmit or has a message to receive will transmit or receive. So there is no schedule of the users, and it purely works on demand. So this works on demand, works on user demand. There is no algorithm, it is purely demand driven. And secondly, no rules specify which station should send next. So if we know which station is currently sending, we cannot infer which station will send next. They are independent variables. So this is why these methods are called contention method. Contention means to fight or to quarrel or to disagree over certain things. So here the stations or the senders are in contention with each other. The stations are in contention with each other. They are fighting over who will get to send the next chunk of data over the medium. So that's why it's a contention method. And however, in random access method, then each of the station will have right to the medium without being controlled by any other station. However, if more than one station tries to send, that is when you have a problem. So one guy wants to send and another guy also comes forward and he says, I will also send data. So then we have an event called collision. Now collision means that two devices, since there is nothing controlling the users, so the two devices randomly decide that they will transmit data and they do it at the same time. So since the medium is able to, since the medium is not channelized, the medium can only handle one packet at a time. So if two users tries to send two packets, then there will be a collision. That is, two data users will send two packets and only one will be transmitted and one will be either destroyed or modified. So frames will either be destroyed or modified. So if two stations like this, two stations and there is only one channel, so he also sends the packet and another guy also sends the packet, but only one of these packets will make it through, whereas the other packet will get destroyed. So in collision there is this one user and there is a channel. Here the channel is visualized as a pipeline. Now this user wants to send a packet and this user at the same time, at time t1, at time t1 this user also decides to send a packet. Now only one of these two packets will get to travel in the channel because this can only handle one packet at a time. Now due to some factor, let's say this packet gets selected, so this packet will get transmitted and move forward in the channel, whereas this packet does not get selected, so it will just come out. It will not get the medium to itself and it will simply get destroyed. So this is known as a collision. Now the main sophistication that goes on in this controlled access algorithms is collision avoidance and collision detection. So we have to somehow manage these collisions. This is the main concern of the CSMA, of the controlled access algorithms. Now we will go through a few contention algorithms, one of which is ALOHA. ALOHA is a, so first algorithm that we will learn is ALOHA. This is a contention method or a random access method. Access, random access or contention method. Contention method. So the first example of such is ALOHA. Now, ALOHA is a Hawaiian word. It's a Hawaiian word meaning hello. So this ALOHA means Hawaiian word for hello. So it basically just means hello. And what is the significance of that? That every user just in pure ALOHA. So there are two types. One is pure ALOHA and another is slotted ALOHA. So in pure ALOHA, the user just sends whenever it has to send. So this is the simplicity of pure ALOHA algorithm. So this is a simple but elegant protocol. The idea is that each station sends a frame whenever it has a frame to send. So every station that wants to send a frame will just send the frame. It will not sense the medium, whether the channel is busy or not, whether other users want to transmit or not. The ALOHA algorithm is not concerned with such things. Whenever a station wants to send a frame, it will send a frame. But the problem with that is, because stations are independently sending frames and the channel can only handle one frame at a time, multiple frames are getting destroyed. So here you can see that station 1 has sent one frame. Now station 1's frame is going on in the medium, but at one point when the station 1 has not yet completed transmitting its frame, station 2 decides to send its own frame, and that's when the collision happens. And also station 3 at some time later in the same window decides to send his frame, and so does station 4. So there is an overall collision here. But in this station 3, you will see this one. This packet will get transmitted because it started when no one was transmitting. At this time, no one was transmitting. And it ended in that time also no one was transmitting. And in the middle also no one was transmitting. So for the entire window, by coincidence, if you get the entire window of time for transmission, the channel is empty. Only then can you avoid a collision. But for that entire window, you are vulnerable. If another station decides to send its frame, you will have a collision in your hands. So now how does this pure ALOHA algorithm work? Because simply sending when you want to send is chaos. It is not algorithm. So the pure ALOHA algorithm has some feedback, and that feedback is that acknowledgement from receiver. So pure ALOHA relies on acknowledgement from receiver. Pure ALOHA. This solely works on acknowledgement from receiver. This is the only collision control mechanism it has in itself. The pure ALOHA protocol relies on acknowledgement from receiver. So a collision involves two or more stations. If all these stations try to whenever a station will send a frame, it will expect a receiver to send an acknowledgement. If it does not get an acknowledgement from the receiver, it will try again. So the ALOHA algorithm, simply put, is transmitter wants to send message, rather not wants to, transmitter just simply sends the message. It does not even think, it just sends the message. Transmitter sends message. Then we arrive at a decision. Has receiver sent acknowledgement? Has receiver sent acknowledgement? If the receiver has sent acknowledgement, yes, then your transmission is complete. transmission done. If not, then you will just try it again. So this is pure ALOHA. So if the receiver sends an acknowledgement and you receive that at the transmitter, that means transmission is over and you no longer need to send the message. But if not, then you will try again and again and again. So this is pure ALOHA. If all these acha, now the thing is, we have relied on acknowledgement, but if you instantaneously retransmit, so a collision involves 2 or more stations. If all these stations resend their frames after the timeout, the frames will collide again. Pure ALOHA dictates that when the timeout period passes, each station waits a random amount of time before resending its frame. This time is called back-off time. So now we get another modification that instead of simply sending, what we will do is resending when we don't get the acknowledgement. We will wait the equivalent of a back-off time, TB. Wait TB. So we will wait this time and then we will send it again. So this is another modification to make the collisions rarer. So we will wait for a random amount of time. Every station will wait for a random amount of time. Now the timeout period is now another check that is made on pure ALOHA is the maximum number of retransmission attempts. So again we have to modify our algorithm. So the thing is, if you send once and you don't get the acknowledgement back, if you send it again and again and again, the thing is, at one point you are clogging the system, but you are not achieving your goal of transmitting the message. So at one point you have to stop, right? So in that case, you are allowed a maximum number of transmissions. So here, maximum number of retransmission. That is, you cannot try till the end of the world. You cannot try till the end of the world. At one point, you have to give up. So here we will first wait TB. Then we will make a decision based on, is K greater than KB? So KB is the maximum number of retransmission attempts. Maximum number of retransmission attempts. So if K the number of retransmission, if K the maximum number of retransmission is not greater than KB, then we will again retransmit the message, because we have not The Google Meet seems to be not working right now. It is showing you are offline despite even though I am online, Google Meet is showing that I am offline. Okay, so we are back. So sorry for the interruption. Now the timeout. So what we were saying that it in, in, instead of just transmitting as many times as it wants, the stations are allotted a maximum number of transmission attempts, and beyond that, it cannot attempt to transmit the same message again. So it has to give up. So what is the algorithm looking like? So if you k is greater than kb, no, then you can retransmit again because you have not reached the maximum number of retransmission attempts. But if yes, then you have to stop. You just have to stop. Nothing to do. Now, the timeout period is equal to the maximum possible round trip propagation delay. So this is an important formula. The timeout period or the backoff period is equal to the maximum possible round trip propagation delay. That is, it is equal to the maximum time that data packet will need to travel from transmitter to receiver and then receiver to back. So this is the round trip propagation delay. So which is twice the amount of time required to send a frame between the two most widely separated stations. So if you will of course take the maximum possible timeout round trip possible propagation delay, which is basically simply the two users that are most far apart. And this the backoff time is a random value which depends on the depends on k, the number of attempted unsuccessful transmission. The formula for TB depends on implementation. one common formula is the binary exponential backoff, which means that r is 0 to 2 to the power k minus 1, where k is the current number of retransmission attempts. So if you are, and the back of time will be basically r into this 2 TP timeout period. So back of time will be r into 2 TP. The TP is 2 TP is the round trip propagation delay. So round trip propagation delay, max round trip propagation delay. Now what is this r? R is from 0, then 2 minus 1, 2 square minus 1 up to 2 to the power kb minus 1. So in effect r is simply 2 to the power k minus 1, which is 2 to the power k minus 1, which is dependent on current, which depends on number of so there are binary exponential backoff in this method. So we will, the number of retransmission attempts will decide how much amount of time you have to wait before you can retransmit. So if you have already retransmitted 2 times, the next time you want to retransmit, your backoff time will be 2 to the power 2 minus 1. So your backoff time will be 3 times the round trip propagation delay. Whereas if you have already transmitted 5 times, then you have to wait 31 times the round trip propagation delay. So as the number of retransmission increases, the wait between retransmissions also increases, which depends on the number of attempted retransmissions. So as you go towards the tail end, so if you have failed already 3-4 times, then the amount of waiting that you have to do increases exponential. So that is why it is called binary exponential backoff. So multiplied by the maximum propagation time or frame time. Now the value of Kmax is usually chosen as 15. So usually in pure ALOHA 15 number of retransmissions are allowed. So the algorithm is send the frame, wait 2 into TP. So if acknowledgement is received, then success. 2 into TP is the round trip propagation time. So this is the round trip propagation time, RT prop time. Now you will wait max RT prop time. You will wait this amount of time after sending the frame. So did you get the ACK? Yes. Then your task is a success, and you may consider your task to be a success. But if not, then you will have to reattempt. But before reattempting, you will increase the counter for reattempts. So K will become from 0, it will become 1. Now at 1, is K greater than K max? So K max is the number of maximum number of attempted retransmission. So if K is not greater than that, at K equal to 1, it usually is not. So you can go ahead and you have to choose R. So R will depend on K. So if you choose binary exponential backoff, R will be 2 to the power K minus 1. So R will be equal to 2 to the power K minus 1 and TB will be equal to R into 2TP. So R will be 2 to the power K minus 1 and TB will be R into 2. This way we will select the backoff our time and then we will wait for that amount of time. Once we have done the waiting, we can send the frame again and then we will wait the amount of round trip propagation time for the packet to go to the receiver and the acknowledgement to come back from the receiver to the transmitter. And if it is true, it is success, or else we will increase the counter of the attempted retransmission and then we will again go ahead till we reach K greater than K max. Once when we reach the maximum number of transmissions, then we will abort if we cannot send the message by then. So this is a pure ALOHA protocol. So here we have a problem that problems we will solve later in the assignment. And next we will come to slotted ALOHA. In slotted ALOHA, what happens is that we have to divide the time into slots, and then it is kind of a time division multiple access, a very primitive one at that. So basically we will divide the time into slots and then we will assign each slot to each station, and the packets can, if the station has to send packets, it can send in that amount of time. So pure ALOHA has a vulnerable time of 2 into TFR. So TFR is the amount of time it needs to transmit the frame from the sender to the receiver, and it needs to get back the acknowledgement. So TFR into TFR plus TFR, 2 TFR. So it needs to wait twice the time before it can get the acknowledgement. Once it gets the acknowledgement, it's done. But once you send the packet for 2 TFR amount of time, you are vulnerable to collision. So this 2 TFR time is very critical. In this time, your packet is vulnerable to collision. So yeah, so in the 2 TFR time, it is very vulnerable for 2 TFR time. So in this, we will divide the time into slots. Each slot will be of TFR seconds and force the station to send only at the beginning of the time slot. So for a particular station to send, it can send only in this beginning of the time slot. And once this station can only send in the beginning, and then once the packet has been sent, for the rest of the time all the stations have to hold their packets and wait for the next slot to arrive. Whenever the next slot arrives, the two stations might again send their packets. Here also we can have collision, because all packets are allowed to send at the start of the time slot. All packets are allowed to send data for the first all allowed to send for the first time slot, for the beginning, from the beginning of the time slot, for the beginning of time slot. So at the beginning, not for, sorry, at the beginning of the time slot. So here we are not controlling anyways. We are just controlling when the packet metro stations can send packet, but we are not controlling which packet, which station will send the packet. So here also, at the beginning of a particular slot, 2 or 3 stations or 4 stations might decide that we will send the packet now. Then you cannot help but have a collision. But since apart from that beginning, apart from that time, beginning time, the rest of the time is collision free, then we can assume that if the more stations do not decide to transmit at the beginning of the slot, that packet will go through. So if you can clear the beginning, at the beginning your packet is getting sent, others are not sending, then your packet is through. For the rest of the frame duration, you don't have to wait. So you don't have to wait in anticipation that my packet will get collided. Once you send the packet at the beginning of a slot and others don't, your packet is guaranteed to go through, because in the middle no one can send the packet. And once they can again send the packet, by that time your packet will be completely transmitted. So as long as other stations do not decide to send at the same starting of time slot as you, you are safe. So because a station is allowed to send only at the beginning of the synchronized time slot, if a station misses that moment, it must wait until the beginning of the next time slot. This means the station which started at the beginning has already finished sending the frame. So if you are at the beginning, if your message is not getting, if you are not getting collided with another packet, then for the your message is guaranteed to go through. So your vulnerable time is now just TFR time instead of 2 TFR. So your vulnerable time is now reduced to TFR. Now what is the throughput? This throughput formula is not, the derivation is not in syllabus. So for the, it can be proven that the average number of successful transmission for slotted ALOHA is G into e to the power minus G. So what is G? G is basically the average. So G is basically the maximum number of bits, maximum number of frames that are getting transmitted at once. So the maximum throughput S max is 0.368 when G equal to 1. In other words, if one frame is generated during one frame transmission time, then 36.8% of these frames reach their destination successfully. So if one frame is generated at a time, then one frame is generated at a time. So the stations are generating one frame at a time. So at a particular instant, only one station is generating the time frame, not others. So at that time also there may be collision, because some other packet, some other station might have a packet that they have already generated but they are waiting. So some other stations might have already generated the packet but they are waiting for their slot. So even then, even if only one frame is getting produced at the beginning of each slot by a station, even then you will have collisions, because other packets might be in the backlog for other stations. So the maximum throughput then is 36.8%. So even if only one frame is getting produced per time slot, then also only 36.8% of the packets will be successfully sent. So this will be all for ALOHA and slotted ALOHA. Now let's go to the worksheet. For pure ALOHA system, find the throughput if acha. So this is G to the power minus G. This formula is for slotted ALOHA. Similarly, for pure ALOHA, ready to go. For pure ALOHA, the throughput is G into e to the power minus 2G, which I think is not given here. So for pure ALOHA, let's write it down somewhere. Pure ALOHA and slotted ALOHA. First is vulnerable time. So vulnerable time is 2 TFR, once for the sent packet and once for the acknowledgement. And here it is TFR. TFR is frame transmission time. Frame transmission time. Next is, after vulnerable time, throughput. Throughput is G to the power minus 2G, and here it is G to the power minus G, where G is the offered load. So if you have done class on traffic that I have taught previously, so you will know offered load. Offered load means basically the number of packets, or number of the rate of generation of packets or rate of generation of data, that is directly proportional to the offered load. So this is basically offered traffic. So the more number of packets get generated, the more is the value of G. So throughput is G to the power minus 2G. So what does throughput mean? Throughput means, here throughput means percentage of successful transmissions. This is the definition of throughput. Throughput is a very general term. It can mean many things according to what your system wants. Throughput is basically the rate of output of the system. So it quantifies the output of the system. So here, what is the output of a multiple access algorithm? To send packets without collision, to send packets to manage multiple users and send their packets to their receivers. So the throughput here is the percentage of successful transmission, and that is given by G to the power minus 2G in pure ALOHA and G to the power minus G in slotted ALOHA. So what is the throughput for pure ALOHA system? What is the throughput? Throughput is G to the power minus 2G. So 1 e to the power minus 2. So e to the power minus 2. E to the power minus 2 is 0.1353. Next, now pure ALOHA is a scheduled access protocol, demand access protocol, random access protocol. So in pure ALOHA, whichever packet wants to send will send randomly. All packets can send randomly. All stations, not packets, rather all stations. all stations can send and receive packets independently of each other. So all stations can send and receive packets independently of each other. This means it is a random access protocol. It is not working on any schedule, neither is it working on any demand. It's working randomly. So the correct answer is random access protocol. Next, question 3. Maximum throughput for a pure ALOHA system. Now, maximum throughput here is g to the power minus 2g. Now, throughput is my g to the power minus 2g. So how will we get the maximum throughput? T equal to g to the power minus 2g. We will simply differentiate it. So let's do dt dg. dt dg equal is e to the power minus 2g chain rule plus g into minus 2 e to the power minus 2g. So this is equal to 0 for maximum. Thus, e to the power minus 2g will simply vanish. So 1 minus 2g is equal to 0. Or g is equal to implies g is equal to half. So maximum throughput will be when offered load is 0.5. So what is the throughput then? The maximum throughput Tmax. Tmax will be g at half. Throughput at half, g equal to half. So e to the power minus 2 into half. 2 and half will cancel. So this will be half e to the power minus 1 or 1 by 1 whole by 2. 1 whole by 2. So correct answer is option C. Is there any doubt till now? If you want, you can ask me questions regarding these problems. 3 problems I have solved. So if you have any problem with these solutions, you can ask me.
No doubt, sir. No doubt.
Okay. Next, under maximum throughput condition, the mean number of times a frame is transmitted in a pure ALOHA system. So under maximum throughput condition for pure ALOHA, we learned that what is pure maximum throughput condition? Maximum throughput condition is Tmax equal to 1 over 2e. This is the maximum throughput. So the throughput is now 1 over 2e. It is constant. So the mean number of times a frame is transmitted is, so here the 1 by 2e. 1 by 2e is the throughput, means the percentage 1 by 2e percentage, or 1 by 2 is the fraction of frames that are getting successfully transmitted. So here we have 1 by 2e will be the maximum number of packets that, by percentage of packets that are getting successfully transmitted. So here total number of packets, whatever the total number of packets is, so only 1 by 2e of them will reach, right? And the number of packets that are getting generated is half packets. So basically in 2 seconds 1 packet is getting generated. So g is equal to, since g is equal to half, so what will be the number of packets that will be generated? The number of packets will be the number of packets will be half into t. So if, because in 2 seconds, so in each second half packet is getting generated. So in t time, half t number of packets will get generated. Now only 1 by 2e percentage of that will get transmitted. So number of packets generated is 1 by 2t, and only 1 by 2et will reach throughput. So number of retransmissions needed retransmissions needed will be this 1 by 2t divided by 1 by 2et. So here this half and half, this t and t will cancel, so it will just be e. So number of times you need to transmit is e, or 2.7. So this is equal to 2.7. So for a packet to be sent, you need 2.7 attempts on average. So of course you cannot take 2.7 attempts, but if you average, it will come to 2.7. Sometimes it's 2, sometimes it's 3, 4, like that. But average is 2.7 attempts. You need 2.7 attempts on average. This is a completely average based calculation. Actual number of packets, actual number of attempts might be 100, might be 1. So if you are lucky, you can send your packet at once. If you are not lucky, you cannot send it in even 100 times. That's why we take an upper cap. We make an upper cap of the number of retransmissions that you can do. Because if you are truly unlucky enough, then no amount of retransmission attempts can make your packet reach the receiver. But this is on average. So on average, you need 2.7 attempts. So the correct answer is 2.718. So here throughputs, here if we look at the particular technical language, you can see throughput in terms of frames per frame time. So of a pure ALOHA system is G to the power minus 2G. Frames per frame time means for each frame time, how many, for each frame duration, TFR, how many frames are actually getting transmitted. So for each frame duration, only S equal to 1 by 2e. What is 1 by 2e? 1 by 2e is basically 1 by 2 is 0.18. So 18.3%. So for each TFR duration, only 18.3% packets are getting transmitted. So 18.3% packets are getting transmitted, and how many packets are getting generated? Half. So 18.3 or 0.18 packets are getting generated, and half packets are getting generated, and 0.18 packets are getting transmitted. So at each frame duration, each TFR, you can reframe this problem as like this. This is another way of solving it. At each TFR, half packets are generated, because offered load is half packets generated. But only 0.183 packets are transmitted. So now instead of this, let's look at like this. If one packet was generated but only half packet was transmitted, how many attempts would you have needed? One packet generated and half packet transmitted. So you will need 2 attempts. So here also we will apply the same logic. So half packets generated, 0.183 packets transmitted. So half by 0.183, this will come to be 2.718. That is easy. So this is another way of looking at the problem. Question number 5. Consider a pure ALOHA system with n identical users. So finite number of users. Assume that the normalized load offered to system per frame is G. Throughput of such a system is. Okay, so assume that the normalized load offered to system per frame means per frame duration time, how many packets are getting transmitted, including retransmitted frames, is denoted by G. So here G is simply not the packets generated, it is the packets that are getting put in the system. So the retransmitted packets means those users who tried to attempt send a packet but failed. Those users will send their packets again, and these retransmitted packets are also included in this G. So this particular G is slightly different from the G that we have been learning about previously, because this G includes the retransmitted frames and is not simply the packets that are getting generated. Now we have been asked to find the throughput in terms of this G, not the G that we have learned about previously. So here this one is a bit tricky. So if there are n users, then for one user the the load is basically G by n. So G is the total load of the system. So each user will have on an average G by n load, traffic load. So for the ith user, what is the probability of what is the throughput? Throughput is simply the probability that the ith user's packet is in system and remaining users are not attempting. So what is throughput for ith user? What is throughput for ith user? It is simply probability of two independent events. One is ith user transmitting. Ith user is transmitting. This is one event. And there is another parallel event that is going on. That is, and all others not transmitting. So two things have to happen simultaneously: all others not transmitting and ith user transmitting. So each one of them has a traffic load of say Gi. So ith user transmitting will have a probability Gi, and all other users not transmitting will have a probability of 1 minus Gi. Now 1 minus Gi is for 1 minus Gj. Now this Gj is another user. So there are n minus 1 such users excluding I. So all those will get multiplied. So that's why there will be a pi. Pi j equal to 1 to n. The only condition is that j is not equal to I. 1 minus Gj. So now Gi, Gjs all are equal to G by n. We are assuming that all have equal load. So pi j not equal to I, 1 minus G by n. Now pi j not equal to I is immaterial, so we will just multiply 1 minus G by n, n minus 1 times. So 1 minus G by n will be n minus 1 times. Why n minus 1? Because for one user it is G by n, for everyone else it is 1 minus G by n. Now if this is the throughput for ith user, for all users what will be the throughput? Since this is a symmetric environment, so all users will have the same throughput. Throughput for all users will simply be n times. All n users is summation I equal to 1 to n. Now if throughput for ith user is Ti, then it is summation I equal to 1 to n Ti. Now for all users this is the case. So since it is summation, so it will just get multiplied by n because all users have equal throughput. So the correct answer is G into g into 1 minus g by n whole to the power n. So g into 1 by g minus g by n to whole to the power n minus 1. Sorry, whole to the power n minus 1. So correct answer is option A. Now, measurements in a slotted ALOHA channel show that 10% of the slots are idle. What is the channel load? So 10% of the slots are idle. Thus, this means that if load is G, then probability slot is idle, that is no one is transmitting, is e to the power minus g. So this is given to be 0.1, 10%. So e to the power minus g is 0.1. So g is ln minus ln 0.1 or ln 10. Ln 10 is 2.303. So correct answer is 2.303. So g is equal to 2.303. Now what is the throughput? Here it is a slotted ALOHA channel. So what is the throughput? Throughput is g e to the power minus g. So here g is given to be 2.303. So 2.303 into e to the power minus 2.303. Now you have to calculate this. So 2.303 into exponential minus. So this will be 0.2302. The correct answer will be 0.2302. So the nearest option is 0.231. So correct answer is 0.231. This will be equal to 0.231. It is basically 1/10 of 2.303 because this is e to the power minus ln 10. So e to the power minus ln 10 is 0.1. So this will just get multiplied here. So this is basically just 1/10 of 2.303. Anyways, that is just a neat trick. Now assume that the number of packets n in a slotted ALOHA system at a given time is a Poisson random variable. So the number of packets that are present in a slotted ALOHA system is given to be distributed as Poisson. Suppose that each packet is transmitted with in the next slot with probability 1 by n hat. So if number of packets are Poisson with a random variable of with a mean of n hat. Now each packet is independently transmitted in the next slot with probability 1 by n hat. The probability that a slot is idle. So here the thing is that number of packets in a slotted ALOHA system at a particular time is given to be n. Now each packet is independently transmitted with a probability of 1 by n hat. The probability that the slot is idle. So if there are n packets in system, slot is idle means that no transmitter has anything to transmit in that particular slot. So if there are n packets, so n packets are getting generated in the system. The probability that the system will be idle, that the probability that the system will be idle is simply, if there are n packets in the system, so all of them will have to decide, they send their packet in the message with a probability of 1 by n. So all of them have to decide not to send their packets. So the probability of not sending their packets is 1 minus 1 by n. 1 minus 1 by n hat. So all of them will have to decide that they will not send their packets. And this will happen with a probability of 1 minus n hat to the power n. Now, there are n packets in the system. So the actual probability of the slot being idle is slot being idle and n packets in system. So these two are independent processes. The number of packets getting generated and the number of packets in system are independent of each other. So two things will get multiplied. One is the slot being idle, which has a probability of 1 minus 1 by n hat to the power n, as is derived. Next is the probability that is the probability that there are n packets in the system. So since it's Poisson, the probability is e to the power minus n hat, where n hat is the mean, n hat to the power n by n factorial. So now, what is the probability that the slot is idle? This will simply be the summation of all the probabilities for all the values of number of packets in the system. So it will simply be the summation over the number of the packets of the system. So 1 minus 1 by n hat to the power n, e to the power minus n hat to the power n by n factorial. So if you take LCM in the bracket, so n equal to 0 to infinity, n hat minus 1 whole to the power n, there will be a n hat to the power n at the bottom and there is 1 at the top, so they will get cancelled. E to the power minus n hat by n factorial. Now let's take e to the power minus n hat out of this equation. So this becomes summation n equal to 0 to infinity n hat minus 1 to the power n by n factorial. Now this summation x to the power n by n factorial, what is this? Summation x to the power n by n factorial, this is nothing but e to the power x. So summation n hat minus 1 to the power n by n factorial is e to the power n hat minus 1. So e to the power minus n hat into e to the power n hat minus 1. So this will become e to the power minus 1. So 1 by e. Correct answer is 1 by e. The correct answer is 1 by e. Option C. Now we have to consider the opposite case, that is the slot is successful. Now but there are, what is the probability that the slot is successful? Now what does slot being successful mean? Slot successful means only one packet transition sends. So there can be three possible outcomes of a particular slot. One is idle, no user, so there can be no user sends a packet. So there can be three outcomes for there can be three outcomes. One is slot. One is slot is idle. This happens when no station sends packet. No station no transmitter transmits packets. Next is slot being successful. And when will this happen? This will happen when only one and only one transmitter sends its packet. One transmitter transmits packet. And what happens when slot is a failure? How does a failure happen in the slot? When more than one transmitter transmits packets. So here we have covered slot being idle, and these three are together an exhaustive set of events. That means it can either be idle or successful or failure. It can not be in any other state. So the probability of these three will add up to 1, because either no or one or more than one packets can be transmitted, but there cannot be negative packets, right? So this is exhaustive. So next is we have to find the probability. Now probability that ith user sends packet and n packets in system. So a particular user, ith user, will send the packet and there will be total n packets in the system. So it is the probability that a particular user will send is n hat by n. Sorry, I mean this 1 by n hat. This is the probability of transmission of that packet into 1 minus 1 by n hat whole to the power n minus 1. Now, this is the ith user. So, for all users, one user sends packet. So, for all users, you just add this probability n times. All users sends packet, one user sends packet. So, basically, among all users, one user sends packet and n packets in system. So this will be n by n hat 1 minus 1 by n hat to the power n minus 1. Now, yeah, this is only the probability of transmission, this part. Into there will be a Poisson e to the power minus n hat to the power n by n factorial. Here also same, e to the power minus n hat to the power n by n factorial. Now how many packets can be in system? We have to take a sum over all of them. So slot being successful is we have to take a sum over all the possible number of packets. So summation n equal to 0 to infinity n by n hat, again n hat minus 1 to the power n. You take LCM and n hat by n hat to the power n will cancel, but n hat to the power n will cancel from the denominator. So here it is n hat to the power n minus 1 e to the power minus n hat to the power n by n factorial. Now you see here denominator we have n hat into n hat to the power n minus 1. So together they are n hat to the power n, which cancels with this. And you take e to the power minus n hat common outside. And here also one n will cancel with the n of the n factorial and we will be left with n minus 1 factorial. So e to the power minus n hat summation n equal to 0 to infinity n hat, sorry, n hat minus 1 to the power n minus 1 by n minus 1 factorial. Now since n is going to infinity, n minus 1 and n are at the limiting condition equal. So this is again n hat minus 1 e to the power n hat minus 1. So this is again e to the power n hat minus 1. So if you add them, again you will get e to the power minus 1 or 1 by e. So the slot being successful and the slot being idle have the same probability of 1 by e. So what is the probability of the slot being a failure? So what is the probability of slot being a failure? Slot is failure. So the other two events in the exhaustive set have both 1 by e probability. So the slot being failure is 1 minus 1 by e minus 1 by e. So 1 minus 2 by e. This is the probability of the slot being a failure. Now, again we go back to the same system and we ask ourselves that there were n packets in the system given an ideal slot. So here we have to find probability of n packets in system and ideal slot. Given ideal slot. So this, how do you break down a conditional probability? You divide the intersection by the base probability. So this is the intersection and ideal slot, n packets and ideal slot, and you divide by that by the probability of the ideal slot. Now, n packets and ideal slot, now both of them have been derived. So what is the probability of n packets and ideal slot? So the probability of n packets and ideal slot. Let's go back. Slot idle and n packet in system. This is n hat minus 1 to the power n e to the power minus n hat by n factorial. So we have derived n hat minus 1 to the power n e to the power minus n hat by n factorial. This is the probability of slot n packets and idle slot. And what is the probability of idle slot? 1 by e that we have derived. So the correct answer is n hat minus 1 e to the power minus n hat minus 1 by n factorial. So this is the correct conditional probability. Now, what is this? Is this Poisson with mean n hat, Poisson with n hat minus 1 or n hat minus 2, or none of the above? So what is Poisson? Poisson is lambda to the power x e to the power minus lambda by x factorial. So here, well, actually there will be no n minus 1 factorial. So this will actually be none of these, not this. I think has a problem. So this will not be Poisson with n minus 1 hat, because for it to be Poisson with mean n minus 1 hat, it has to have n hat minus 1 to the power n. Oh, sorry, yeah, n hat minus 1. Yeah, this is Poisson with mean n hat minus 1. I'm sorry, I missed the power. Yeah, n hat minus 1 to the power n e to the power minus n hat minus 1 by n factorial. So this is Poisson with mean n hat minus 1. You can compare, lambda is n hat minus 1, so it's Poisson with mean n hat minus 1. So our correct answer is option B. Now last question. Consider the system described in question 8. Probability that there were n plus 1 packets in the system given a success. probability n plus 1 packets given slot is success. So this one will be, again we have to take the help of conditional probability formula. So now n plus 1 packets in the system, what is the probability of that? It's just Poisson. So e to the power minus n hat into n hat to the power n plus 1 by what is the probability? N hat minus 1 to the power n e to the power minus n hat by n factorial. So it will be n hat minus 1 to the power n plus 1, because there are n plus 1 packets. E to the power minus n hat minus 1 by n plus 1 factorial. This is the probability of n plus 1 packets and successful slot. Now this will get divided by 1 by e, which is the probability of successful slot. So sorry, this will be e to the power minus n hat. This will be e to the power minus n hat. So you take this e to the numerator, n hat minus 1 to the power n plus 1, e to the power minus n hat minus 1 by n plus 1 factorial. So this is again Poisson. This is again Poisson with a mean. So instead of n, we have n plus 1. So we can just write n plus 1 as some new variable p. So n hat minus 1 to the power p, e to the power minus n hat minus 1 by p factorial. So the main variable is this mean. This is the parameter of the exponential, and this is just an independent variable. It can be n, it can be p, it can be c, doesn't matter. What matters is this mean. So this is a Poisson distribution with a mean n hat minus 1, just like the previous answer. So you can see that a slot being successful and a slot being idle have the same distribution. So this will bring today's class to an end, and you may join again next week, same time from 6 p.m. Tuesday. Thank you. You may leave the call.